Hello guys, in this tutorial we will go over three standard techniques that you may consider to estimate how many clusters you want to consider for your data if you're thinking about k-means as an algorithm or technique to group your data. So let's get to it. So clustering basically, again, in one of the previous tutorials, we talked about k-means, the big idea behind k-means, how to apply k-means to the iris data set. Okay, one thing that I highlight in that tutorial was that k-means in particular, one of the big disadvantage is that you need to set how many clusters you want to consider for your data. In some cases, you may have an idea how many groups you want to consider. In other cases, you may have no clue how many groups you want to consider. So in this tutorial, we will go over three standard metrics that we could consider to estimate how many clusters you need to consider for your data. Okay. Again, keep in mind that this is just a pure data-driven techniques. Okay. And it's going to be pretty much a brute and force approach because, again, we're going to try different number of clusters, and depending on the metric that we are evaluating, we will select what it seems to be the appropriate number of groups or the appropriate number of clusters. Okay, so let's get to it. So as I mentioned before, or as I mentioned in one of the previous tutorial, clustering is about finding groups in your data. And again, is an unsupervised learning. Basically, that means that there is no target variable. Okay. All right. So we talk about k-means, and again, at the very beginning of that algorithm, we need to set how many groups we want to consider. So if you have no clue in terms of what is the value that you need to consider, here are three standard metrics that you may consider as a way to estimate how many groups you need in your data. Okay, so the first one is called the Calinski Harabasz score. The second one that we will cover is the Davies Bouldin score, and the last one is the silhouette score. Okay, again, keep in mind that these are only three metrics. There are a few others, but then these are kind of standards that I see used by practitioners in different applications. Okay, so let's go to the first one, the Calinski Harabasz score. Okay, so this is also known as the variance ratio criterion. Okay, because it combines, in some sense, some of the variability between clusters and the variability between clusters. Okay, so it's a ratio of two expressions. So then this is what you have. This is, in some sense, this is a numerator. Okay, and then here what you have is one of the denominator. Okay, so here, right here, as you can see, you see mu k, that's the mean of each of the clusters, or the center of each of the clusters. Mu is just the overall mean. Okay, so it's comparing the centroid of each of the clusters with the overall centroid of the standard data. So when you look at that expression, it looks like the variance, okay, the variance formula. So if you remember your stat classes, it looks something like this, right? From 1 to n of xi minus x bar squared. So it looks very similar to that. So then that expression basically is quantifying the variance across the clusters. Okay, and what you have here is, in some sense, quantifying now the variance between each of the clusters, because here we have xi, and that represents the observation that belongs to cluster I in some sense. Mu k is the centroid of cluster k. Well, k is going to vary from 1 to k, so depending on how many clusters we have. So then that expression, in some sense, is quantifying the variability that we have between each of the clusters. Okay, So that's basically what this metric is computing, is comparing the between clusters dispersion with respect to the what they call it intercluster dispersion. Okay, so that's one metric that you may want to consider to as a way to estimate how many clusters. Okay, now here is the rule of thumb. Okay, the rule of thumb is the following. Okay, the smaller, or excuse me, the higher the score is, the better. So if you consider different number of clusters, right? So then let's say first you cluster the data into two clusters, and then you compute the Calinski Harabasz score, and then you compute, then you cluster the data into three clusters, compute the score, four clusters, compute the score, and so on. So after you finish going through all the different number of clusters that you want to consider, so and then you compute the corresponding CH scores, so then you will select the number of clusters that maximize the Calinski Harabasz score. That's basically the rule of thumb. Okay. So again, there is no much sophistication here. It's just a brute and a force approach. Okay. And that will be the case for all of the metrics that we're going to cover in this video. Then the next one is the Davies Bouldin score. Okay, so this is another metric that you may want to consider to estimate the number of clusters for your data. Okay, so basically what this metric does is the following. Okay, so it's the average similarity between clusters. Okay, where the similarity is a measure that compares the distance between clusters with the size of the cluster themselves. What is the rule of thumb here? Is a lower value for the Davies Bouldin score relates a model to better separation. So if you are considering the Davies Bouldin score as a way to estimate your number of clusters, so you're going to consider a different values for the number of clusters. You compute the corresponding Davies Bouldin score, and then you will select the number of clusters that minimize the Davies Bouldin score. Now let's briefly talk about what this metric is doing and what this metric is measuring in some sense. Okay, so there are a few components here that we need to cover first. So then first we have SI, and that will be the average distance between each point in cluster I and the centroid of the cluster. Okay, so for each cluster, and then it's going to be the average of the distance of all of the points with respect to the centroid. Then Dij is the distance between centroids I and J. Okay, and then we have Rij, which is Si plus Sj divided by Dij. Okay, now let's look at the actual metric, right? Because Rij, so then that's part of this formula we see it here. So then the Davies Bouldin score is just the average, right? Over I goes from 1 to K, and the maximum when I is, notice here that I is different than J of Rij. So basically here is just the average, okay, of Rij. And in some sense, Rij is measuring the similarity between cluster I and the most similar cluster. Okay, and then in this case, the most similar is defined as is computed using the Euclidean distance. Okay, so the closer the two centros are, the closer the two centros are, the more similar those two clusters are. Okay, so basically that's the reason why you see the I different than J. So then is quantifying similarity between two clusters and the similarity inside of each cluster. Okay, so that's basically what the Davies Bouldin score is. Again, so if you want to use this particular metric as a way to estimate the number of clusters, you will consider different values for the number of clusters, and then the number of clusters that minimize the Davies Bouldin score, that will be the selected one. And then the next one is the silhouette score. So this is another popular metric that you may consider to estimate the number of clusters. So again, so this is another metric that in some sense is measuring how good the clustering results are. So, and the three metrics that we cover here, in some sense, they are measuring how good the clustering results are. So in essence, what they want to see is they want the clusters or the observations that fall in the cluster, that they are close to each other, and that the two clusters that they want to be as far away from each other as possible. Okay, so the silhouette score is a metric that is going to be computed for each observation, okay, in the data. And then at the end, so once each observation has a corresponding silhouette score, then you just average those silhouette scores, okay? And that value is going to be some number between -1 and 1. The closer the average silhouette score is to 1, the better results or the better clustering results, okay? So now let's briefly talk about what the silhouette score is, okay? So then the formula for the silhouette score is the following. So then again, this is just the formula that is going to be applied to every single observation in the data, okay? So it's bxi minus axi divided by the maximum of those two, okay? And what is axi? AXI is the average distance between the point and all of the points, or the point I and all of the points in that cluster, okay? And BXI is the average distance between point XI and the points in the next nearest clusters, okay? So you compute that for all of the observations. And again, once you have the AXI and the BXI for all of the data points in the data, then with those two, you can compute the corresponding silhouette scores for all of the observations in the data. And then at the end, you just take the average of those silhouette scores, and that will be the value that you will use to estimate the number of clusters. Okay. And again, the idea here is you cluster the data into two groups and then compute the corresponding average silhouette score, then 3 corresponding average silhouette score, and so on. And then at the end, you select the number of clusters that maximize the silhouette score or the average silhouette score. That's it, okay? So these are three standard techniques that you may consider to estimate how many groups you may want to consider for your data if you have no clue in terms of how many groups you need, okay? So there may be some scenarios in which, again, that you don't have a clue. So then here are three data-driven techniques, okay? So this is just pure data. We are, in some sense, we are exploiting the data to see, okay, how many groups do I need here, okay? All right, so then now let's take a look at these three measures in action. So we're going to continue using the IRIS dataset. So then this is the same dataset that I used in the previous two clustering tutorials. So first we start by reading the data. Okay, again, so here we have four different measurements on iris flowers. And then this represents the species associated to that iris flower. Okay, so what we want to do is we want to estimate the number of clusters using the three metrics that we just reviewed. Okay, but before we do that, first we will start by defining what are the features that we're going to use for clustering purposes, okay? For that, so first we need to load sklearn pre-processing. So I like to use a standard scalar. You don't have to use a standard scalar all the time, but as I mentioned in the previous two tutorials, especially when you are relying on a technique that relies on the Euclidean distance calculation, you need to make sure that all of the columns are on the same scale, okay? So we import standard scalar, we import k-means because we're gonna be using k-means, and here we're going to define the data for clustering purposes. So in this case, we're going to use again all of these columns, okay? So from the data frame, we just want to drop this column, the column species. So drop columns equals species, axis equals to 1, columns equals. All right, and then we're going to standardize the data. So we're going to use a scalar, or the standard scalar, excuse me, and then we scale the data with fit transform. Okay, so up to that point, we define the data, we standardize the data, and then we're ready to estimate the number of clusters for k-mean purposes. So first, we're going to start with the Calinski Harabasz score. So for that, we're going to use scikit-learn, okay, and then under metrics, they already have that implementation. So we start with from sklearn metrics import Calinski Harabasz scores, okay? So again, as I mentioned before, so then this is just a brute and force approach. So then we're gonna cluster the data first into 2 clusters, then 3 clusters, then 4 clusters, and so on, okay? In each case, we're gonna be computing the corresponding Calinski Harabasz score, okay? So, and then at the end, what I like to do is I like to create just a very simple chart that shows us how the score, or in this case, the Calinski Harabasz score, is changing for the different number of clusters. So for that, I will import matplotlib. All right, so then let's create a simple list just to store the scores. So this is how you define a simple list. And then for I, so we need a for loop here. So let's say we go from 2 to 10. So here we're defining the k-means model. So notice that on each iteration, the number of clusters is going to be changing. Okay, so that's the iterative variable, right? I is changing, and then nint equals to 20, which is random state. So up to that point, so then these two lines will cluster the data into I clusters, and then here we compute the Calinski score. Okay, for that, so we need the actual data and the cluster labels. Okay, and then here we're extracting the labels, so you can compute the Calinski Harabasz score. And then once that is computed, then we store it in the list that we just defined here. Okay, and then at the end, what we want to do is we want to plot the results. Okay. Okay. Okay, so I think that will do it. So let's run this. And here we have the results, okay? So on the x-axis, we have the different number of clusters that we are considering. So we go from 2 all the way to 10. And then here on the y-axis, we have the Calinski Harabasz score, okay? So what was the rule of thumb when it comes to the Calinski Harabasz score is the higher the value is, the better. Okay, so again, let's quickly go back to that. So here, right, Calinski Harabasz score, the higher the score is, the better. Okay, so in this case, we see that at least based on the Calinski Harabasz score, that the suggested number of clusters is 2. Okay. All right. Now let's go over the second metric. The second metric is the Davies Bouldin score. Okay, so it's going to be very similar to what we have here. So we start with from sklearn metrics, import Davies Bouldin score, DB score. So we start looping through that. So we define the model. Okay, so K means the number of clusters is going to be changing from 2 to 10. NINT is 20. Then here we apply that to the data. Then here we extract the labels or the cluster labels, and then with the data and the cluster labels, we compute the Davies Bouldin score, and then we append it into the list that we create here, and then we're going to visualize the result. Okay, almost there. All right, so now let's run this. All right, when it comes to the Davies Bouldin score, again, going back to the notes, the Davies Bouldin score suggests what? A lower value it shows a better result, right? The smaller the Davies Bouldin score is, the better. So in this case, again, so here we have the result associated to two clusters, and that's the one that minimizes the Davies Bouldin score. So again, based on the Davies Bouldin score, we should cluster the data into two groups. That's basically what we're learning from this. Okay. And the next metric that we may consider to estimate the number of clusters is the silhouette score. So it's going to be very similar to what we did in the previous two cases. So from sklearn metrics, import silhouette score, silhouette score. Okay, so then the number of clusters is going to be changing. And then here we're pulling the labels, so we need to have that extra variable there. So, and then plot those results. All right, let's run this. All right, in the case of the silhouette score, it's always going to be some number between -1 and 1. And basically, the closer that value to the closer the value is to 1, the better. So in this case, the number of clusters that maximize the silhouette score is 2. Okay. So in this case, it just happens that the three approaches uh, suggest that we should cluster the data into two groups. That is not going to be the case all the time. Okay, so I work with data sets in the past that in some cases, one approach says, for example, I'm just making this up. Okay, so there's one approach says 3, and then the other two say 5. Okay, so then at that point, what do you do? So in my case, at least I like to have simpler solutions. And when it comes to clusters, so then the smaller the number of clusters you consider, the simpler the solution is. Okay. Again, keep in mind that this is a data-driven approach. Okay. So again, what I always suggest is if you have no clue in terms of how many clusters you need to consider for your data, I mean, here are three options. Okay. In real life projects, so if you're working for a company, right, and then part of the project or part of the analysis has to do with finding segments or doing some clustering analysis on the data set. So what I recommend there is just you need to talk to the stakeholders and see what may be appropriate in terms of the number of groups for the data. Okay, because again, it could be the case that you are running this type of approach and it's suggesting 15 clusters or suggesting 20 clusters. Okay, um, if you're going to be presenting results associated to 20 clusters or for an industry project, it may be a little difficult to explain that solution. So in real life projects, again, when there is a stakeholder involved, so make sure that you talk to he or she, get some guidance in terms of how many clusters need to be appropriate. Based on my experience in the industry, typically some number between 3 and maybe 8. Because anything greater than 9 or 10, I mean, it becomes really, really difficult to explain that solution, right? In terms of you have so many groups, Yeah, so it gets difficult to explain that process. Okay, but if you have no clue, again, if you have no clue in terms of how many clusters you need to consider for your data, here are three approaches that you may consider, at least as a starting point. Okay, all right, so that's all I have for this video. See you on the next one.